For quite a while, people have envisioned what life might be like in other universes. Thanks to the James Webb Space Telescope, the most remarkable telescope in existence, that question can finally be investigated. While observing the closest star system to us, Proxima Centauri, which is just 4 light-years away, researchers have observed some exceptional oddities from one of the planets in the system, Proxima B. These peculiarities, called fake lights, have perplexed the best minds in astrophysics. But what are they? Do these lights suggest the presence of intelligent life on the planet? Join us as we investigate the James Webb's alarming discovery of city lights that could change everything. The only life that we are currently aware of is on Earth. Starting from the beginning of human civilization, people have questioned whether there is life somewhere else in the universe. To complete such an interstellar hunt, American cosmologists Jill Tarter and Thomas Pearson launched the search for extraterrestrial intelligence, SETI project in 1984. The charitable goal was to assemble spaceborne radio transmissions. Radio waves can travel farther and are therefore more prone to be identified by the 42 radio telescopes that make up the exceptional Allen Telescope Array in the Californian Overflow Mountains. However, in the past 30 years, no obvious alien signal has been found. Following that, the James Webb Space Telescope's successful launch boosted the journey to explore a range of unseen planets orbiting distant stars. As the largest telescope in the world, drifting approximately 1 million miles from Earth and equipped with incredibly sensitive indicators, it has the potential to uncover huge discoveries. 20 years ago, there were no known planets outside our planetary system. However, since then, more than 4,000 exoplanets have been discovered orbiting different stars. According to NASA, the universe may contain trillions of exoplanets. The earliest indications of something going on under the surface, past our solar system, might be seen as extraterrestrial vegetation. The Galileo spacecraft, on its course to Jupiter, turned its gear back toward Earth and saw a clear sign of the presence of plants, recognizing the vegetation red edge, VRE, biosignature, a blend of red and infrared lights reflected by plants. For example, a planet like Earth covered in wilderness ought to have a strong VRE signal easily identifiable. The JWST will measure the VRE of faraway, Earth-like planets in the habitable zone around stars, which could give significant indications of something going on under the surface in the exoplanet environment. When sunlight crosses a planet's star, the JWST might have the option to detect it as it enters its atmosphere. The missing frequencies would then be found through spectroscopy, as molecules and atoms in the air absorb specific frequencies, creating a characteristic fingerprint that the JWST can recognize. This technique might be used to determine the composition of the atmosphere and whether life is possible. Life could exist on Earth-sized planets with climates similar to our own, characterized by a combination of oxygen, nitrogen, and carbon dioxide. By searching for elements that aren't generally present, one might be able to identify intelligent life. For instance, chlorofluorocarbons, CFCs, produced for use in refrigeration and cleaning products, would almost certainly be recognizable to outsiders checking Earth's atmosphere from afar. If the JWST found CFCs in planetary atmospheres, that would be an obvious sign of progress. However, life on exoplanets probably won't look like life on Earth by any means. Sometimes even natural living things like extremophiles, species that can survive in conditions where other living things would die, can seem alien. This group of life forms, primarily microorganisms, can endure extreme conditions such as heat up to 250 degrees Fahrenheit or solid acid with pH levels under 3. Since planets like Earth are bound to support life more than those with extreme temperatures or acidic conditions, it may be wise to start with those first. Prime candidates could have temperatures that permit liquid water to exist on their surfaces and orbit a stable star. Our Sun is a yellow G-type star. These stars are more uncommon and usually have shorter lifespans. However, in our universe, the probability of finding planets orbiting red dwarf stars, which are more frequent, cooler, and dimmer than our Sun, is higher. This long time span allows for the development of life and evolution to produce complex organisms. About 40 light-years from Earth, the TRAPPIST-1 planetary system will be the subject of the JWST's first mission. It rotates around a quiet red dwarf star with 7 Earth-sized rocky planets. 3 of these rocky planets, situated in the so-called habitable zone, could have liquid water on their surfaces. Notwithstanding its smaller and colder mass compared to our Sun, the TRAPPIST-1 star emits light that is similar to that of Earth. Because of the close orbit of its planets, the most obvious opportunity to observe city lights outside the nearby planetary system is Proxima Centauri. A red dwarf star that is 4.25 light-years from the Sun. Proxima is multiple times fainter than the Sun, so a planet would need to be multiple times closer to it than Earth is to the Sun in order to support life based on liquid water. In August 2016, astronomers discovered a planet with 1.3 Earth masses in this habitable region, a Goldilocks-like zone, where the light power is perfect for melting water. Proxima b orbits Proxima Centauri, but the fact that Proxima b is tidally locked makes it a potentially airless, dead planet. Given that it orbits its red dwarf star just 4.6 million miles away, this close orbit exposes it to strong solar winds that can completely strip away its atmosphere. However, Proxima b does get sufficient daylight for temperatures and liquid water like those on Earth. Due to its proximity to the star, Proxima b is believed to be tidally locked, meaning it always shows the same side to the star, similar to how the Moon does in relation to Earth. Proxima Centauri is around 18% the mass of the Sun and emits much less light than one might expect for a planet so close to its star, only about 5% of the Sun's intensity. It might seem like a scorching ash, but liquid water could exist on Proxima b as long as the planet has an atmosphere to retain heat. Since the total energy reaching it from the Sun is just 65% of what Earth gets, the planet is not particularly friendly to life. It is likely tidally locked, meaning it always faces the same direction toward the star, creating a permanent day and night side with significant temperature changes. The planet also receives 100 times as much high-energy radiation as Earth does, including X-rays and ultraviolet light, because of its proximity to Proxima Centauri. Proxima b is also bombarded with high-energy particles during star flares. Unless it has a protective magnetic field like Earth's, conditions for life may not be positive. Despite these harsh conditions, Proxima b could still be a more pleasant world. Unfortunately, models suggest that the atmosphere of tidally locked planets might be prone to rapid collapse due to the freezing out of volatile gases on the night side. Our planet's atmosphere can be replenished by volcanic activity, and for planets with strong magnetic fields, this atmosphere is less likely to escape. Since we know nothing about Proxima b's volcanic activity or magnetic field strength, we cannot even guess whether the planet has an atmosphere. However, since an atmosphere suggests the presence of oxygen, and the two together suggest the possibility of life, we are eager to know if Proxima b has a modern civilization. It could have solar panels covering the day side to produce power to light and warm the evening side, which would otherwise be too cold and dark for comfortable habitation. The discovery of Proxima b has triggered a race to determine whether it crosses its star's face as seen from Earth. These transits would allow researchers to determine the planet's size and mass, which would enable them to estimate its density and confirm its rocky composition, providing information on the materials used to form those rocks. During a transit, starlight could disclose the nature of the planet by passing through its atmosphere. However, the probability that the orbit will be aligned correctly for researchers to see a transit is only 1.5%. The star's tendency to flare also complicates matters. Cosmologist David Kipping of Columbia University says the star is unstable. As stellar heat causes a rocky planet to absorb sunlight and re-emit it as infrared light, rocky planets produce a distinct kind of infrared radiation from stars like Proxima Centauri. Moreover, the James Webb Space Telescope was designed specifically to study infrared light. Proxima b's infrared signature is key to identifying the planet's atmosphere. Additionally, the infrared portion of the spectrum has strong advantages over the Hubble Space Telescope, which might allow the JWST to detect city lights on its night side, even if they are as weak as those currently used on Earth. The JWST could identify artificial lighting as long as it is confined to a frequency band much smaller than the star's light. Proxima b's day side might be heavily covered with solar panels reflecting starlight. As Proxima b orbits its star continuously, the day and night sides are indistinguishable, with cool night lows following daytime highs. The temperature difference between day and night depends on whether the planet is made entirely of bare rock or whether air and water both circulate heat. If there is no atmosphere, Proxima B's dayside and nightside temperatures will contrast more since the dayside will radiate all the energy it gets from Proxima Centauri as a black body. The night side would look like a frozen wasteland. If the temperature difference between day and night is less pronounced, we can infer the future of space exploration and the search for life beyond Earth holds immense promise. The James Webb Space Telescope, JWST, stands at the forefront of this groundbreaking journey. Proxima B's potential to harbor signs of intelligent life, including artificial lighting, opens up a new realm of possibilities for discovering extraterrestrial civilizations. The discovery of city lights on Proxima B would be a monumental breakthrough in our quest to understand the universe and our place within it. Whether it's the detection of biosignatures, unusual atmospheric compositions, or even artificial lights, the JWST could one day reveal startling new insights that change our understanding of life in the cosmos. The potential for finding life beyond Earth has been one of the most captivating questions in science. As we continue to explore the cosmos, the technological advances in astronomy and space exploration bring us closer to answering this age-old mystery. The James Webb Space Telescope, JWST, represents the cutting edge of this exploration, providing astronomers with the tools necessary to uncover new clues about exoplanets that might harbor life or exhibit signs of intelligence. What makes the JWST particularly exciting is its ability to peer deeper into the universe than ever before. Its infrared capabilities allow scientists to analyze the atmospheres of exoplanets in exquisite detail, helping to identify chemical compositions that could suggest the presence of life. The telescope's ability to observe distant planets in various wavelengths of infrared light allows it to gather more data than previous telescopes, revealing potential biosignatures or artificial signs of life, such as city lights. Another crucial factor in the search for life is the study of planetary habitability. This concept centers around finding planets that are in the so-called habitable zone, where conditions might allow liquid water to exist. Liquid water is a vital ingredient for life as we know it. However, while the habitable zone provides a guideline, it does not guarantee that life exists on these planets. Other factors such as the planet's atmospheric composition, its magnetic field, and its exposure to radiation play a crucial role in determining whether it could support life. The habitable zone of a star depends on the star's size and temperature. Red dwarf stars, such as Proxima Centauri, are much cooler than our Sun, which means that planets in their habitable zone would need to be closer to the star to maintain temperatures suitable for liquid water. However, these stars have a downside. They are more prone to emitting harmful flares and intense radiation, which could strip away a planet's atmosphere or prevent life from thriving on its surface. This is why studying the specific conditions on planets like Proxima B is so important. Even though the planet resides in the habitable zone, the extreme radiation from its parent star could pose a significant challenge for life to evolve. Moreover, researchers have also begun to explore the idea that life might exist in forms that are radically different from what we are familiar with. Extremophiles, organisms that thrive in extreme environments such as volcanic vents or acidic pools, suggest that life could potentially survive in harsh conditions elsewhere in the universe. The idea that life could exist in environments previously thought to be uninhabitable expands the range of planets that could support life, making the search even more intriguing. The JWST's advanced tools could help us detect these more subtle signs of life, even if they don't resemble the forms we know. The detection of artificial signals or technologies beyond Earth presents another layer of excitement in the search for extraterrestrial life. While the discovery of city lights on Proxima B would be groundbreaking, there are other technologies we might look for. For example, radio signals, electromagnetic pulses, or other types of artificial emissions might offer the first signs of intelligent civilizations. Such findings would not only provide answers to the question of whether we are alone in the universe, but would also raise profound questions about the nature of intelligence, technology, and civilization in other star systems. It is also possible that some exoplanets might harbor civilizations that are far more advanced than ours. If artificial light or other signs of technology are detected on a distant planet, scientists would need to assess whether these civilizations are still alive, whether they are capable of interstellar communication, or whether they have long since disappeared. This raises the possibility that we might one day receive a message from another civilization, or that we might find evidence of a long-extinct one. In the broader context of space exploration, the JWST's findings could have profound implications for humanity's future. Understanding more about how life arises and evolves on distant planets can provide valuable insights into the origins of life on Earth. Additionally, discovering the signs of advanced civilizations might inspire us to develop new technologies or reconsider our place in the universe. The next decade will be crucial in answering some of the most fundamental questions about life beyond Earth, and the JWST is positioned to play a pivotal role in this journey. The prospect of discovering city lights on Proxima B or finding signs of extraterrestrial intelligence invites us to think beyond our planet and consider the broader implications for our understanding of the cosmos. Whether we find biological life, artificial intelligence, or simply new clues about distant worlds, these discoveries will likely reshape our perspective on the universe and our place within it. As we continue to explore the stars, the search for life in the cosmos remains one of humanity's greatest endeavors, and the JWST is poised to be a central player in that quest.